Hi folks, I had a really good question the other day about what happens if two planes are intersecting in a line, and when we kind of arbitrarily set our z value, where we say we're just going to take the position vector from where the line intersects the xy plane and the direction vector where there's a scalar multiple that gives a z equals 0. What if that position vector doesn't exist? What if you get something where the z value actually does not, or the line does not intersect the xy plane, so it's parallel to the xy plane and z can never equal 0. So I'm going to show an example of this where I'm just going to try it and see what happens. So if we tried our standard way and just said let z equals t, now normally we would take these equations of the planes that were given. So I've kind of worked backwards and made up two equations that do intersect in a line, but they do not, that line of intersection is parallel to the xy plane. So we would do elimination to, eliminate one of the variables, x or y, and then we would sub in our z equal t. So we'll try that. I'll try and eliminate the x's. So I would get 20x minus 12y plus 28z plus 156 equals 0. And oops, actually I've got a wrong value in there. This one, when I made up these equations, I copied that down wrong. I think that should be minus 7z, so this would be minus 28z. Then when we go through, we're going to do our elimination. We're going to subtract that from the first equation. So 20x minus 20x is 0x, and negative 12y minus negative 12y is 0y. And 7z minus negative 28z is plus 21z. And 72 minus 156 is negative 84. And that all equals 0. So you can see normally we would be eliminating one of the or the other of x and y, and then we'd sub in the z value to solve for the other x or y in terms of t. But here we've eliminated both of our x's and our y's. So we're just left with a linear equation that we can solve for z. So we get 21z equals 84. And then dividing, we actually just get z equals 4. So this means that the equation of the line of intersection has a constant z value of 4. We are not going to be able to change that. So in order to figure out a relationship between x and y, if you have a constant z value, the x and y end up forming what looks very much like a Cartesian equation of a line in R2, because essentially they are in just two dimensions. They're not on the typical xy plane, but they would be on the plane z equals 4, that line. So I'm going to take my equations again. 5x minus 3y minus 7 plus 39 equals 0. And 20x minus 12y minus 7. Whoops. That should be 7z up there. Minus 7z again, plus 72 equals 0. And I'm going to eliminate the z's because I know the z value is just a constant of z equals 4. So I'm going to subtract here. That will eliminate the z's, and we'll end up with just a relationship between the x and y values. So here I'm going to do 5 minus 20 in the x's, so I get negative 15x. And then negative 3 minus negative 12, or plus 12, is plus 9y. The z's will be eliminated. And then I have 39 minus 72 is negative 33 equals 0. So we can see that this is just actually a line that would be in R2, but it's not on the XY plane, it's on the plane Z equals 4. So it's 4 units moved up from the XY plane. So we can do a few different things here. Some people may be more comfortable working in, for instance, y equals mx plus b form. Or some people may, and you could kind of convert that to y equals mx plus b and draw a little sketch to get a direction vector. But I know the normal to this line will be negative 15 and 9, right? That means the direction vector of that line that would be perpendicular will be, it's kind of like negative reciprocal. It will be 9, 15. Swap the signs and you can check that it would be one where m dot n equals 0. So you could see we've got negative 15 times 9 plus 9 times 15. That's going to give you a dot product of 0 because the normal would have to be perpendicular. So now I have a direction vector. Then I could just sub in to get any point. And I'm just going to kind of try and pick something that works well. So I might pick, if I chose, let's see, I can just need any point on this line. And I'm kind of trying to look for one that's going to work out to whole number values. And I think, so this is find any point. I'm just going to say let x equals negative 1 because I think that that'll give us a nice y value. So plus 9y minus 33 equals 0. So 15 minus 33 plus 9y equals 0. So that's negative 18. So 9y equals 18 and y equals 2. So the point on this line in R2, the line here, would be the position vector, so negative 1, 2, plus t times the direction vector of 9 and 15. But we know that we actually have this in R3, and we know that the z has that constant value of 4. So I can extend this to say, well, okay, my actual position vector in R3 would be negative 1, 2, and 4, because z is a constant value, plus t, and I'm still going to have the 9 and the 15 from the x and y components of the direction vector, but I know I'm not going to have any change in z. So the z will not change at all, and that will give us the equation of the line in R3 that has a constant value for z of z equals 4, and otherwise is just kind of directly above this line in R2 that we could find from that original equation.